So in the previous class, we have gone with the basics of number system and how we can represent different numbers by using the conversion methods, and also we have seen what are different types of codes are there. Continuation to that, we will start with the basic gates and how the Boolean algebra explains the digital expressions and digital functions. We will see these next. So basic gates we will see. So what are the basic gates? So here any digital logic is there. So digital are basically we have seen different type of number systems. So one is a binary. So in binary we are having two different bits or two different digits, 0 and 1. So all the computer systems or digital systems basically use 0 and 1 combination to represent any data, or it performs any mathematical operations based on the 0 and 1 only. So these zeros and ones are going to be written in terms of some variables. So some variables are like a, b, x, y. So these are the different variables, and there are some relation between these variables. So these relations are explained in terms of basic gates. Okay, so how the operations on these variables are going to be performing, or the relation between these variables are basically explained in terms of basic gates. So basic gates will be the circuits, digital circuits that will be used to represent the logic relations. Okay, so here there are different type of gates are there. So AND, OR, NOT, NAND, NOR, XOR, and XNOR. So out of this, NAND and NOR are called universal gates, and AND or NOT, these are called basic gates. These are called NAND and NOR are universal gate. So why it is called universal gate? Because this NAND and NOR can be used to implement any of the gate. It can be used to implement any of the logic gate that is available in digital circuits. So that's why this NAND and NOR are called universal gates. XNOR will be used where the complex mathematical functions or mathematical circuits or any complex circuit, digital circuits need to be implemented. So XOR are used basically for complex digital circuits. If we want to have the complex logics, we will be using XOR and XNOR. But AND, OR, and NOT are the basic gates, and NAND and NOR are the universal gates. So I think you might have gone with the these gates previously. So we'll just take an overview like how these gates are there, what are the basic functions of it, and expressions we will just see. So AND gate is there. So this is the symbol of AND gate. Here two different inputs will be there and one output will be there. So its relation between the inputs will be x dot y, that will be f, and the truth table with the combination of inputs and output will be here. So this will be 1 only when both the inputs are 1. When both the inputs are 1, then only the output will be 1, otherwise it will be a 0. The OR case, it is represented by plus sign. So here output will be 1 in all the cases. It will be 0 only when both the inputs are 0, then output will be 0. Inverter is the complement. Whatever input we are giving, the output will be the complement of the input. Buffer is whatever the input we have provided, the output will be the same. So if it is 0, output is 0. Input is 1, output is 1. This is called buffer. So in inverter, if we remove this bubble, it will be a buffer circuit. Next is an AND. So here two inputs are there. So it is AND with a NOT. Okay. So we are having AND gate with a NOT gate will be your NAND gate. So whatever the AND truth table is there, we will be putting an NOT gate. So invert of that will be our output in case of NAND. Similarly the NOR. So NOR is the OR gate with a inverter. So this is your NOR gate. So this is the truth table. XOR gate is having the relation like it will be 1 when the inputs are different. So here the inputs are different. X is 0 or Y is 1. If X is 1, output Y is 0. So if inputs are different, then output will be 1. If inputs are same, the output will be 0. If inputs are same, output will be 0. So this is how you can remember the concept. So here in exclusive or XOR gate, output will be 1 only when both the inputs are different. If both the inputs are different, output will be 1. The opposite will be the exclusive NOR. Okay, so exclusive NOR is the complement of XOR. So if XOR is there, so XOR complement will be XOR. This is the XOR complement of XOR will be your XNOR. So its output will be, it will be 1. It will be 1 when both the inputs are 1 or 0. That means if both the inputs are same, then output will be 1. So it is opposite to this. So this is the basic gates. So I think you might have gone with this. So next basically we will see the Boolean algebra. Boolean algebra is the algebra related to Boolean functions. So Boolean is, we have already seen there are different number systems. In that we are only considering the binary number system, and this binary number system is having zeros and ones. So these zeros and ones will be represented by some variables. Okay, so these variables are nothing but like any variable, whatever arbitrary value or variable we have taken. Okay, so any variables are there, this can have the possible values, that is 0 or 1. So each variable can have a possible value that is 0 or 1 only. Okay, so that's why these variables are called Boolean variable, or any operation that is involved with these Boolean variables will be called Boolean algebra. If we are adding two A and B, that can store a value of either 0 or 1. Okay, and suppose this is equals to C plus D. If this is the case, then we can say this is an Boolean expression. This is an Boolean expression. So we need to represent, or we need to use this variable that is storing either 0 or 1, and we are going to relate these variables with each other. Okay, use of any relation between these variables are going to be dealt with the Boolean algebra. So whatever the relation or whatever the operations, mathematical operations we are going to perform on these variables will be dealing with the Boolean algebra. Okay, so Boolean algebra binary case, here it is having different properties or different theorems related to this. So in that, how these variables are related in relation to this Boolean mathematical functions, that is plus is there, dot is there. Okay, so these plus and dots and zeros and ones, how these variables are related, it is explained by with the help of some theorems and postulates. So that we will see, these are the theorems. Okay, so here theorems related to it is, if A is a Boolean variable and if we are going to add 0 to it, it will be A only. If A is there, we are going to AND with a 1, it will be A only. So these are the different theorems. So I think you might have gone with this in previous also. So A plus A is there, so it will be giving out A only. A into A or A AND with A will be giving out A. So this is important, that will be used for simplification of the expressions. So A plus A bar is there, that will be giving out 1. So how it is like, any value is there, suppose a is there, it is having 0, a is 0, then we need to do a plus a bar. So a is 0 given and a bar is complement of 0 means 1, so it will be 1 only. So the OR of these two will be 1 only. So this is the case, first case. Suppose a is equals to 1. In that case, so 1 plus a bar is 0, is equals to 1. So this is letting us a plus a bar will be 1 always. So this will be used most frequently in simplification of the expression, and also a dot a bar. If a is there, we are going to dot with dot means ANDing. We are going to do AND with a bar. It will be giving out 0. So, and there are further theorems are there. You can just go with it. I think you might have known this also. So here, what is like to one theorem is given like x plus 0 is equals to x, and here it is x dot 1 is equals to x. So these are like the given theorems. These theorems explains the dual nature or duality property. So we will see what is duality. So duality property means what we do in finding a dual function. So if any expression is given x plus 0 is equals to x, it will be converted to x dot 1 is equals to 1. So this will be its dual. So in dual property, what we do is, for dual expression, to the dual expression we check for some steps in the sense like we are going to check like how we can convert expression to its dual. So to check that, we will convert AND to an OR, or if OR is given, we need to convert it to AND. So AND will be converted to OR, or OR will be converted to AND, or like it is AND is dot will be converted to plus, or plus is converted to dot. So this is the first case. Second is, if we want to convert to dual, if 1 is written, we need to convert it to 0, and if it is 0 is written, we need to convert it into 1. In the third case, whatever the variables are there, okay, so variables will be left as it is. Okay, so we can write like keep variables as it is. So if any expression is written, suppose this one is, so it is x plus x y is equals to x. So this is an theorem. So if it is written like x plus x y is written, it will be equals to x only. So this is a theorem, and if we want to find out its dual, then what we need to do is we need to convert AND to OR operation, or wherever it is dot, we need to convert it to plus. If it is plus, we need to convert it to the dot. So x, if it is plus, we need to convert it into dot. If it is next is x dot y is written, so x y means x dot y is written, so we need to convert it like x dot will be converted to plus y. So this was together, so we will be making it together is equals to x. Okay, so this is how we will be converting. So it can be represented like x, in bracket it is written, dot is there, so it will be written equivalent to like this. So this will be the dual of this. So sometimes in the questions, objective type questions, it can be asked like an expression will be given, you need to convert it into a dual expression. So how this is how we will be converting, and just consider this one. So here x plus 1 is equals to 1 is written. So if we want to convert it into dual, we need to replace plus with dot or with AND. 1 will be converted to 0, okay, and variables will be kept as it is. So variable will be kept as it is, plus will be converted to dot, 1 will be converted to 0, and equals to 1 will be converted to 0. So its dual of this expression will also be an theorem. So as this was the theorem, if anything is added to 1, the result will be 1 always. Why? Because any variable that we have considered, it can be having a value 0 or 1, and if we want to add something to 1, either it is 0 or 1, the result will be 1 itself. This is a theorem. Okay, its dual expression will be x dot 0 is equals to 0. That means if we are going to multiply or going to AND with 0 to any variable, the result will always be a 0. So in the previous gate, we have already seen the ANDing with a 0 will always be resulting to the 0. So this is the different theorems that are related to Boolean variables. So these expressions or the theorems are named like the x complement with a complement will again result to the same x variable. So this is called involution. Similarly, if x plus y is equals to there, we can write it as y plus x also. So it is commutative. That means we can change the location of these variables, then also the result will be same. So this is called commutative. We can commute the variables from here to here, means we can change the position of the variables. There will be no effect on the expression, its result. Associative means we can have x plus y plus z. So it is written, it is associative like y plus z is there. That means y or z is associated further and then x is added. In the next time it will be equals to like if all are the ORing operation, we can do x plus y, means we are associating x and y together and then ORing with z. It will be resulting in the same expression. Distributive means whatever the x is there, x dot y plus z is there. So dot means and is there. So this and with y plus z is there. That means we can just distribute this and operation to y and z separately. So x dot y plus x dot z. So we are distributing the AND operation. So this is distributive property. De Morgan's theorem. This is most frequently asked question is on De Morgan's theorem is if x or y to be complemented, then its result will be x bar or x complement and y complement. Or its opposite is like if x dot y is there or x and y is there, its complement will be x dot x bar plus y bar. That means x complement or y complement. So this is De Morgan's theorem, most frequently used. Absorption theorem, it is x plus x, y is there, so its result will be x only. So it is absorbing the y component. So that's why it is absorption theorem. Its complement is this also. So these theorems can be used for simplification of the expression if it is given. So one more point I would like to say here. So if this is the dual expression, another one is complement. So how the dual and complement is different, we will see that. So if we have an expression, we can convert it to a dual expression by keeping this into mind. So in case of conversion to a complement expression, that means complementing an expression, there is a very little difference. In considering the complement of any expression, the first step is really converting AND to OR. It was similar to the dual. That means a dot will be converted to plus and plus will be converted to dot. The second is again here we will be converting 1 to 0 or 0 to 1. The third one is in the dual calculation, dual expression writing, we were keeping the variables as it is. But in complement, if we want to implement write the complement of any expression, we need to complement each variables. The difference between dual and complement expression is all the steps are same. The only difference is in dual we are keeping the variables as it is, but in complement we need to complement the variables also. So for example, suppose any expression is written like x plus xy is equals to x. This was the expression. If we want to have its complement, so its complement will be, we are going to change the plus or to and, so it will be, and also we need to complement the each variable. So if we want to complement the each variable, it will be x bar. We can write either x bar as it is, or we can write it as x dash. So x dash is x complement dot x y complement will be equals to x complement. So this is how we will be writing the complement function. But in case of writing a dual, if you want to write the dual function of it, so whatever x is there, variables will be same, and plus it is x dot x dot y was there, it will be plus y is equals to x. So this will be your dual expression of this. In complement, x bar dot x dot y is it is, but we have implemented then is complement, so we will be further expressing it like it will be x dot x complement dot, again expanding this, it will be x complement, it was dot, then it will be plus y complement. So how this has obtained? So this has obtained by using De Morgan's theorem that was explained previously. So you can just see De Morgan's theorem, it was x dot y complement will be x complement plus y complement. The relation between dual expression and complement is, this is how we can do the complement of any expression or any variable. It is a given relation between variables that will be used to write the complement function. So in complement we need to complement the variables also, but in dual we need not to complement the variables. We will be keeping the variables same. This is the basic of Boolean algebra. So next we will see what is mean term and what is max term. So any variable is there, so the relation between any variables is given by Boolean functions. So a Boolean function will be like, if any function is there, suppose f, so if x is there, f is there, it is having the relation between x, y bar, z. Suppose this is the relation, so here x, y and z are the Boolean variables, so this is the relation. So with respect to f is equals to x plus y bar z, if we want to represent it in terms of gates, if we want to represent it in terms of gate, we can represent it in terms of gate directly. So here first we will be converting this one, so y bar z is there, so y bar we need means y complement, so we will be using not gate, so it is y complement, and now it is and, it is an and operation, so we will be anding it. If we are anding it, we can get y dash y complement dot z. Now it is or, so we will be oring it with the x, so final output that we will be getting is x plus y dot y bar z. So this is the how a function of Boolean nature can be implemented with the help of basic gates. So we can use basic gates to implement the function of any Boolean. So this is a Boolean variable. With the help of Boolean variables, we are able to write a function, and this function can be implemented with the help of basic gates. And also, if we have a truth table, if this is the truth table, from there also we can get a function. So there are suppose two different functions is there, that is depending on x and y and z variables. So these are x, y and z input variables are there. With respect to that, we have two different functions f1 and f2. if we want to find out the f1, so f1 will be written in terms of like whenever there is 1 is coming in f1, we will be writing its equivalent relation of the input variables. So f1 is 1 in this case, like x is 0, y is 0 and z is 1. So in that case, the first it will be written like if x is 0, so we will be writing x bar, then y is 0 means y bar, z is 1 means z. So this will be representing 0 0 1. Okay, so next is if this is 1, so in that case x is 1, y is 0 and z is 0. So we can write x, y is 0 is there, z 0 is there. So it is 1 0 0. It is representing the relation between x and y and z for the function f1. Plus for the next we can write x, y bar, z. Plus next one x, y, z bar. For last x, y, z. So it represents 1 0 1 1 1 0 1 1 1. So this is the function f1. Similarly, we can write the function f2 also. So in the case of f2, you can get it is 1 at this point, this point, this point, and here. So we will be writing the expression for f2. So f2 will be similar to that x, y, x bar, y bar, and z. So it is 0 0 and 1 plus x, y, z. X is 0 1 1, so it is 0 1 1. X, y, z, it is 1 0 1 0 0. So 1 means it will be not bar, here bar will be there. The next one is x, y, z, here 1 0 1. 1 0 1 is there, so it will be 0 is here, so it will be bar. So f2 will be written like this. So f1 is written like this. These terms, so the terms that we have used, so this is one term, this is another term. So these terms are called mean terms. This is mean terms. So mean terms are like whatever the relation of input variables is giving you out, the output will be the mean terms. So these variables, relation between these variables and giving you out to a function f1 will be the mean terms. So these are another set of mean terms, and these mean terms combinedly is going to give out the function f2. So these are called mean terms. So with the help of these mean terms, we can write the any function. So any function is there, f1. So these mean terms we can write in terms of like here plus is there, plus is there, plus means each mean term is being added. So f1 can be written by like summation. So summation stands for adding. So we are going to add. So this is 0 0 1. So 0 0 1 means in decimal it is 1. So we can write like summation of small m 1 because it is 1 representing 1. M1, this is 1 0 0. So 1 0 0 represents 4. So M4 comma this is 1 0 0 1 0 1, that is 5. So M5, this is 1 1 0, that is M6, 1 1 1, that is M7. So it is summation of mean terms M1, M4, M5, M6 and M7. So the function f1 can be represented by this summation of the different mean terms. So different mean terms will be represented by small m with its representation. It is represented by 0 0 1, so it is 1. Or we can further simplify it like summation. If it is summation, it is understandable like inside it there will be mean term. So instead of writing m1, m4, m5, m7, m6, we can directly write 1, 4, 5, 6 and 7. So f1 will be represented by the summation of mean terms that is representing 1, 4, 5, 6 and 7. And also here, to further simplify, it is written like if f1 is there and f1 is taking the variables x, y and z, three different variables. So f1 is written like x, y, z. That will be equals to summation mean terms 1, 4, 5, 6 and 7. This is how we can represent a function, that is f1. Similarly, we can represent the f2 also. So to represent f2, it is again the sum of mean terms. So as it is sum of mean terms, we will be making a summation of mean terms m0, 1. 0, 0, 1 is there, so it is 1. Again m0, 0, 0, 1, 1, it is 3. 1, 0, 0, m4, m5. So we can further write it in terms of x, y and z. So x, y and z, they are input variables. Input variables are x, y and z. It will be written like summation of 1, 3, 4, 5. We can directly write 1, 3, 4, 5. So this is how we can write any function in terms of its mean term. Okay, so I hope you have got the point. So some questions are there based on the simplification. So we have gone through the theorems, different theorems. So if an expression is given like x in bracket x complement and or y, if this is the written, we need to simplify it. So we can just simplify it further with the help of expressions or theorems we have got in previous. So it is x in bracket x complement plus y. So this is x to be multiplied inside, so it is called distributive. We are distributing the x with inside the bracket. So x multiplied by x bar plus x multiplied by y. So x multiplied by x bar is equals to 0. That is it is already given in the expression. So x into x bar will be 0 plus x and y. So finally we will be getting xy. So this is the simplified expression value of the given expression. Okay, so its simplified value will be x into y. Similarly, different expressions are given. You need to just simplify it. So we can use the properties of different theorems that we have gone in the previous slide, that will be helpful for explaining the simplification of these different expressions. So x plus x complement y is there. So we can simplify it by considering the distributive again. So this is why it is distributing these two. So we will be further or we can further take it like we can consider it x plus x bar. So it is like here we have just distributed it, like it will be distributing it with this, and then so similar to this one, it is again distributive with respect to plus, that means with respect to r. So r x will be r with x bar multiplied by x will be r with this, and x plus x bar is equals to 1, we already know, is equals to x plus y, this one multiplied by x plus y will be x plus y itself. So this is a different expression and its simplified solution is given. Just go through it. The next one is here we need to write the dual property or dual expression, right? Dual and complement. So different functions are given, you need to write dual and complement functions. So if f1 is written like x bar y z bar plus x bar y bar z, you need to find out the dual. So to find out the dual, what we need to do is we need to put variables as it is. We need to just replace dot with plus and plus with dot, and if 0 is there, that will be represented by 1. 1 is there, it will be replaced by 0. So there is no 1 and 0, so we will just need to check for dots and plus. So if this is x bar dot y bar y dot z bar, so whenever there is dot we will be replacing it with a plus, and here it is plus, so we will be making it a dot, and then this will be your dual. But in case of complement, with the help of complement, we need to replace dot with plus or plus with dot. Along with that, we need to complement the variables also. So we will be complementing the variables also. If we will be complementing the variables also, so it is x bar, it will be represented by x. Okay, so this is how we will be representing the complement. The second function is there, f2, we need to write it here. So again from there also, if you want to find out the dual, in the dual, x will be dot will be represented by plus, plus will be represented by dot, but the variables will be same. There will be no change in variable, but in complement form, along with the changing dot into plus, plus into dot, we will be complementing the variables. Each variables we will be complementing. So these variables are called literals. Okay, so I hope you have got. So okay, so in the previous we have just seen what is mean terms. So mean term is we are going to get different variable terms that is going to explain a function. Each variable term is called the mean terms. Next one is max terms. So again here we will see what is a max term is there. So in the above function itself we can just see what is max term. Okay, so we can just see what is max term. So max terms is the complement of mean terms. This is the truth table that we have already seen in the previous concept. So again, if we want to find out the max terms, so in the previous we have just seen like one way is just to complement the mean terms, but the basic step to find out the max term is in mean terms. Whenever there were ones in a function, we were considering put with relations that is going to give us the mean terms. Similarly, if we want to find out the max terms, for max terms we need to consider terms where function of 0. Whenever there is a function of 0, so whatever these relations are there, that will be giving out a max. Any function can be written either in terms of min term or max term. So if we want to write f1 in terms of max terms, that will be equals to instead of summation we will be doing the multiplication. That means we can just write here. So if we want to write in terms of max terms, we will be writing is like x, y and z is there. So it is like whatever the function is there, we will be writing it like x. So instead of just it will be complement is means in the previous one we were writing x bar, y bar and z. So here we will be writing x, instead of dot we will be making it plus y plus z, and it is 0 0 0. So if it is 0 0 0, we will be making it this one. Okay, so the next one is instead of making the plus we will be multiplying it. So it is 0, this is x plus y plus z. It is, so whenever there is 1 we will be complementing it. So whenever there is 1 we will be complementing it. So this is how we can represent max terms. Till now we have seen different Boolean variables, and based on the Boolean variables some theorems and postulates we have seen. Next we will see what is a Boolean function is there, And based on a Boolean function, how we can implement a Boolean circuit, a circuit with the help of different gates. So first we will see what is Boolean function. So Boolean function will be defined in terms of Boolean variables. So if any Boolean function is there, f, and if this function is defined by different input variables or Boolean variables, that is suppose x, y plus yz plus zx. So this is a function that is defined in terms of their inputs. Okay, so there are three different inputs, x, y and z. So it can further be defined like f will be the function of x, y and z, that will be the input variables or the Boolean variables. Based on that the function will be defined. So this is the relation of different Boolean variables to define a function. And if we want to implement this function but with the help of a logic gate or a circuit, we want to implement a circuit diagram with the help of this Boolean function. We can implement like it is x dot y is there, so it is an AND. So we will be using an AND gate, and here x and y will be the inputs. So this is your x, y. So next one is again another AND function is there, y dot z. So we will be using another AND gate, that is y and z. It will give us y, z. Next is another AND gate, that is z and x. It will be giving you out zx. So whatever the outputs of AND gates we have obtained, so these terms we have got. Now we need to add it. Add means we need to use OR gate. So now we will be using OR gate to get the sum of all the product terms. So this final expression here, that will be equivalent to our function, that is f, it is xy plus yz plus zx. So this is how, based on a Boolean function, we can implement a circuit diagram. Another example we can see. So another example, if we want to see, so this is, suppose we want to draw the logic diagram of the Boolean function. So this is a function. Here f depends on x and y variables. So we can further write like f is the function of x and y. So it can be represented like that. So it is x bar y plus x y bar. So if we want to implement the function, in the previous one we have seen there is no use of bar. That means that we don't require any and NOT gate. So we have implemented like that. If you want a NOT gate to implement, so here x bar is required, so and also x is required. So we have considered a line for x, and with an inverter we have considered this is x bar. Similarly y, because y and y bar both are required, so y with inverter we have got y bar. So we have now got x, this is x line, x bar line, y bar line. Now the first term is x bar y, so we need to use AND gate to get the x component and the y bar component, and we will be ANDing it. Similarly we need to get x bar and y, and we need to AND it. Whatever AND we have performed, the output of AND will be OR to get the function. So this is how we need to implement a logic circuit or logic diagram with the help of logic function or Boolean function. And Boolean function will be in terms of the Boolean variables, and these Boolean variables, can be taking the value 0 and 1. That's why it is called Boolean variable. A variable means any value it can take, but it is Boolean variable, so it will be taking only 0 and 1s.